which is 2e, and we had a look at kinematics last year. And so the basic link is just going to be from the table at the top. We have S of t. Intuitively, of course, S represents displacement. Silly convention, right? And the rate of change of displacement is going to be velocity. And the rate of change of velocity, the rate at which velocity changes, is acceleration. So if we differentiate S of t, we will get V of t. If we differentiate V of t, we will get A of t. Now just quickly, the difference between distance and displacement. All right, this is an important distinction for us to make because we will be asked both about distance and displacement. So let's say here's John, and John walks 10 meters to the east. All right, we're recapping displacement, and then 5 meters back to the west. The total distance he has traveled is 15 meters, but his displacement is 5 meters. Displacement is distance from the point of origin. Okay, so that's an important concept for us. All right, there's a couple of dot points listed there that are important to comprehend. They'll pop up in the questions. So let's get straight into this question. We have the displacement, the position. The position of a particle moving along the x-axis is given by the function t to the 3, take 9t squared, plus 15t. All right, part A. Draw sign diagrams of the particle's acceleration and velocity functions. So velocity is the derivative of displacement. And so we're just going to differentiate the first function here. We'll have 3t squared, take 18t plus 15. Now we can get a sign diagram straight from there in our calculator, but whenever the opportunity arises, I'm always going to draw out these algebraic skills, right? So one way we can find this sign diagram is by factorising it. T squared takes 6t plus 5. So we have two numbers that multiply together to give us positive 5. And when we add them together, we get minus 6. That'll be t take 5 and t take 1. Which means the roots are 1 and 5, right? So as far as the velocity sign diagram goes, I'm going to draw it over here. It's going to look like this. We have 1 and 5. It's a quadratic that has a positive a value. So we would have positive, negative, positive. All right, now that sign diagram is perfectly acceptable for you to get that from your graph. All right, so we differentiate here, we draw the graph of it, and then we get the sign diagram. We can g-solve the roots, we can observe when it's above and below. Again, I'm just going to draw out algebraic skills where we can. So that's the velocity sign diagram. Now the other thing is that whenever we're doing kinematics, we only consider positive values of time. So I've got a line here drawn at 0. All right, we don't consider negative values of time. We're not going to rewind time. We're only thinking about time moving forwards. So that's the sign diagram of the velocity function. Let's draw the sign diagram of the acceleration function. So acceleration is the derivative of velocity, the second derivative.
So if you get a root that's negative,
we don't put it on the sign diagram. Very good. Yep. So when we differentiate this function, we'll have 6t take away 18. This is the equation of a line. We can start to see that its root would be 3. If we put the number 3 into it, it would make it equal to 0. So the acceleration sign diagram has a root of 3. It's the equation of a line. It has positive slope, so it's looking like that. It's going from beneath to above, negative, positive. Now I'm just going to label both of these. This is A of t, and this is our B of t. Good, so that's part A complete. Getting a couple marks early on just by differentiating and drawing sign diagrams. I suppose the difference between 3e and what we've been doing is that here we've given context to the original function. All right, so if the original function represents displacement, then the rate of change of displacement is velocity. So we can give it. Okay, find the positions and time when it changes direction. Okay, so velocity is speed plus direction, right? So what we notice here is that we have positive velocity. Now, by convention, so for mathematics, positive velocity means moving to the right, negative velocity means moving to the left. So what's going on here is we're moving to the right until we get to time is 1. At time is 1, it's not moving. The velocity has a root. The velocity is 0. So we're moving to the right until we get to time is 1, and then we're moving back to the left until we get to time is 5, and then we're moving to the right again. So you can think of a party, maybe like a tennis ball going back and forth. Okay? All right, so the question says, find the particle's position and time when it changes direction. So we can see here, because there's a change in sign, okay, it's gone from positive velocity to negative velocity, it changes direction at t is 1. So this is our answer to part B. Changes direction at t is 1. Now, we're asked for the position of that. So that means we need to find s of 1. All right, so we want to know what's its position when it changes direction. Now, again, whenever we have to do these kind of calculations, my advice is let's process that right at the end, okay? Or right when we absolutely have to. Because what we're doing is we're on a roll. We just got our pen in hand, and we're going, all right. It also changes direction when time is 5, because it goes from moving to the left to moving to the right. So that means in a moment we'll have to calculate s of 5. Okay. Part C. Don't forget that you've left a blank thing there, by the way. Part C. When is the particle's speed increasing? Okay, speed is increasing. Now I'm going to take you to the third dot point where it says important points on page 46. Speed of an object is the magnitude of velocity. Now magnitude, that just means the size, the length. It means how big it is. So speed is the magnitude of velocity. If v of t and a of t have the same sign, then speed is increasing. If they have opposite signs, then speed is decreasing. So this is why the question's got us to draw these sign diagrams. We can observe the intervals where they have the same sign. So between 0 and 1, v of t is positive and a of t is negative. So speed is decreasing over this interval. They have opposite signs. Between time is 1 and time is 3, both of them are negative. So that means speed is increasing because they both have the same sign. If they have the same sign, speed is increasing. So for C part 1, speed is increasing when, and we'll list that as an interval, 1 is less than t is less than 3. So that's when they're both, v of t and a of t are both negative. So what that means is the speed is increasing to the left. It's accelerating to the left. All right? And then they're both positive for values of t larger than 5. So we can write and t larger than 5. Okay, that's when they both have the same sign. All right. When is velocity increasing? Velocity is increasing whenever acceleration is positive. So, velocity, and let me make that really obvious as to why that's the case. All right? If you think about, if this is our function, if v of t is our function, a of t is the derivative function. And so what we have is this explains the slope of v of t. And so we have v of t is decreasing and then increasing. The velocity is increasing for values of t larger than 3. Really good. Okay, part D. Find S of 6 and draw its motion diagram. So S of 6, I'm going to list up. This is D, isn't it? So we've got S of 1, we've got S of 5. Let's find S of 6. Now, we're almost ready to draw the motion diagram. We've got sort of these three features. what I'm going to do now is sketch this function, and I might even show you another feature we have on our graphics calculators as well. Always want to show as many pictures as we can. So let's all go to graph mode and sketch this function. So we have x to the 3, take 9x squared plus 15x. Now it's probably really easy to just trace along it and input the x values to get when x is 1, when x is 5, when x is 6. And the other thing we obviously need for a motion diagram that's implicit here, whenever you're drawing a motion diagram, is you need s of 0. That's its initial position, all right? Its displacement when time is 0. We have its displacement when it changes direction at s is 1 and s is 5. And we have the displacement when time is 6. Okay, so we can sketch it and we can G-solve from there. But what I want to show to you is if we go back to the main menu, and we're going to go to table. We haven't gone in there before, have we? Table. Table is number 7. 1, 2, 3, 4, 5, 6, 7. So, if we go into table, notice here how we have 3 columns. We have x, y, and y dash. All right, so it's telling us the x value, the y value, and the y dash value. Now, I might come around and answer a specific question if you have one in a sec, Claire, but for now, what we're going to do is we're interested in the points s is 0, s is 1, s is 5, and s is 6. So we can change those x values. 0, all right, 1, 5, and 6. Okay, and I'll draw up here what I've got. I've got when s is 0, y is 0. When s is 1, y is 7. When s is 5, y is minus 25. And when s is 6, y is minus 18. Okay, anyone, any problems? No, sure. Danny? Makes sense? So all we do to change it is just start typing. So if you type in 0 there, yep, and it tells you the corresponding y value. So you can go down and change those. Darcy, good? Ella? Yep. You go? Excellent. Okay. So that can be another strategy. Like I'm just showing you ways that we can do these things. All right. So to draw. So firstly, let's answer what it said. It said find s of 6. Done. Okay. So we've done the first part. Now it says hence draw a motion diagram. Now for a motion diagram, you need all of the important points. Those are where it begins and where it ends. So we need its position. And then we need any places where it changes direction. And we know it changes direction at these 2 points. We've already found them. So then all a motion diagram is a horizontal axis. And we're going to put on this axis those extremities. Okay, the furthest that it goes to the left is negative 25. So that's going to be here. And the furthest that it goes to the right is positive 7. We've got a 0 in there, the point of origin, and we also have minus 18 as a point of interest. All right, so those are the 4 points that we're interested in on the diagram. So we've got our axis, we draw an axis there to scale, of course, have a nice scale. And then all we do is we go, all right, well, it begins here, and initially it's moving to the right. All right, so initially it takes off to the right, and after 1 second, its displacement is 7 meters. All right, then at 1 second, it stops and changes direction. The particle starts moving back to the left, and it keeps going to the left until it gets to minus 25. At minus 25, a displacement of minus 25 after 5 seconds, it stops, it changes direction and starts moving to the right. And we're asked to stop after 6 seconds, even though it would continue moving to the right following that. So here we have all of these positions. We have t is 0, t is 1, here we have t is 5, and here we have t is 6. And this describes its position on an axis where it is. Okay, so that's the sine diagram. Okay, now there's actually 3 parts here. It says, find S of 6, done. Draw the motion diagram, done, gorgeous. Hence, find the total distance travelled in the first 6 seconds. Not the displacement, we know it's displacement after 6 seconds. Its displacement is minus 18. But what's the total distance? Well, it's travelled 7 there, so you can think of it as travelled 7 units that way, and then it's travelled, well, from there to there is 25, so we have 7 plus the 7 to get back to the origin, plus 25 to get to there, so 7 plus 7 plus 25, and then from 25, negative 25, back to negative 18, that's another 7, isn't it? So that gives us 46 units. And the question does stipulate a unit for us. We just go right back to the start. Meters. Very good. Okay, so we've answered all of those parts successfully. So to draw a motion diagram, we find the important points. That's where it's changing direction. All right, we won't go through the second example just yet. Let's get you guys to rip into the exercise, and we can leave that second example for either after recess or another time. So stop there. It'll start pretty easy, the exercise, and then it'll get harder from